Welcome to AI Paper Podcasts. Today we're diving into a paper that's really making waves. It's rethinking how we train neural networks.
Yeah, it's pretty fundamental stuff.
Forget everything you thought you know about backpropagation, maybe even forward propagation.
Yeah.
Because we're talking about a new method called NoProp.
That's the one. The paper is NoProp, Training Neural Networks Without Backpropagation or Forward Propagation by Kinyu Lee, Yu Te, and Razvan Pascanu. And, well, it's a really intriguing piece of work.
Definitely. It could have some pretty significant implications for, how we approach deep learning research.
For sure.
Okay, so let's get right to the core of it, maybe for folks catching this quickly. In under a minute, here's what you absolutely need to know about NoProp.
Go for it.
Right. So NoProp is this novel training method. It completely ditches both backpropagation and forward propagation during training.
Which is kind of mind-blowing.
It is. It takes inspiration from diffusion and flow matching. Basically, each layer learns to denoise a noisy version of the target independently.
So layer local learning?
Exactly. Now, this is a big departure because it means NoProp doesn't learn hierarchical representations, not in the traditional sense anyway.
Right, that's a key point.
But surprisingly, the paper shows it achieves superior accuracy, and it's more efficient than other backpropagation-free methods on standard datasets like MNIST, CFIFAR10, CFAR100.
Yeah, the results are pretty compelling.
Plus the way it assigns credit, how the learning happens, it could pave the way for more efficient distributed training.
Okay, that's the quick summary. Now, what's fascinating here is the fundamental challenge this paper is actually tackling.
Right, the why.
Backpropagation, it's been the workhorse of deep learning for ages, right? But it comes with some, let's say, inherent baggage.
Like what?
Well, think about the biological aspect. Does the brain really do a synchronized forward and backward pass? Probably not, right?
It's unlikely.
Then there's the practical side. The memory needed to store all those activations for the backward pass. That can be a real bottleneck, especially for huge models.
Oh, definitely. Memory usage is a big deal.
And the sequential nature of gradient propagation, it makes parallelizing training, pretty complex.
I have to wait for the gradients to come all the way back.
Exactly. And these aren't just theoretical quibbles. They impact how we scale and apply deep learning. They can even lead to problems like interference or catastrophic forgetting.
Right. So, okay, these researchers looked at these limitations and basically asked, what if we could train a network in a totally different way?
A fundamental rethink.
And that's the space NoProp is exploring. The central idea, like we said, is each layer learns to clean up a noisy version of the target label, all on its own.
Like a little noise-canceling engine.
Yeah, exactly. Trying to isolate the true signal from the static. And here's where it gets really interesting. During the training phase, they don't even need to do a standard forward pass of the input data through the entire network.
Which is, that's a truly radical shift. Instead of that error signal going all the way back.
Right.
Each layer is just focused on mastering its local denoising job tied to the output. By using ideas from diffusion models and flow matching, it's a completely different learning paradigm.
And it's not just a theoretical curiosity.
No, absolutely not. The paper shows pretty convincingly that NoProp outperforms existing attempts at backprop-free training. And it seems simpler, more robust, and more computationally efficient too.
All right, let's get into the nitty-gritty then. How does NoProp actually pull this off? Can you walk us through the core methodology?
Absolutely. So NoProp introduces this idea of a sequence of noisy intermediate states, let's call them 0, Z1, all the way up to ZOT.
Okay.
You can think of 0 as pure noise or a completely garbled version of what we want. And ZT is the final state, hopefully clear enough to make a prediction from.
Makes sense. From noise to signal.
Kinda. Then the paper defines two crucial probability distributions, P and Q.
P and Q. Got it.
So P describes a stochastic forward process. Imagine how you might gradually add noise to a clean signal, moving from one state to the next, getting noisier.
Okay, the noising process.
And Q is the variational posterior. Think of Q as our best guess, given the true label and the input data, about what those intermediate noisy states might have looked like.
So the reverse direction, kind of?
Sort of, yeah. It's about inferring the path given the endpoint. These are formally laid out in equations 1 and 2 in the paper.
And this forward process P, the way noise is added, it's not like a standard neural net forward pass, you said.
Exactly right. Equation 3 shows this. It's described as something maybe akin to a residual network, but with a key twist.
Okay, what's the twist?
At each step, T, we're injecting Gaussian noise. So the state Z depends on the previous state, Z21, plus the output of a residual block U and this added noise.
And that block, it sees the input x.
Yes, crucially, it's conditioned on the input x. So ZT is a function of ZT1, this block U, which takes both ZT1 and the original input x plus the noise.
Ah, okay, so the input x feeds into every step.
That's the key difference from standard deep nets, where layer n only sees the output of layer n1. Here, the input x informs each step of this noising process.
Interesting.
The authors also mention you can interpret this whole process P as a conditional latent variable model, where the z's are hidden variables connecting the input x to the output label y.
Okay, so that's P, the forward noising process.
Yeah.
How do we actually learn the parameters of these blocks, the UTs? That's the core, right?
Right. This is where the variational formulation and the evidence lower bound, or ELBO, come in. You'll find this in equation 4.
ELBO, okay, standard variational inference tool.
Exactly. Think of the ELBO as, well, a tractable proxy. Directly optimizing the likelihood of predicting the right label is often too hard.
Right.
But we can optimize this ELBO, which is guaranteed to be a lower bound on that true likelihood. So maximizing the ELBO pushes the actual likelihood up.
Makes sense. How do they define Q to make it work?
Right, so to make this feasible, they fix the variational posterior Q to be a specific, well-behaved Gaussian process. It's a variance-preserving Ornstein-Uhlenbeck process, shown in equation 5.
Okay, that's a specific mathematical term.
Yeah, it gives a concrete way to model the transitions between these noisy states in the reverse direction, conditioned on the target label y. And using standard Gaussian properties, they can write down the distributions Q(t)(ti) and Q(t1y) explicitly. That's equation 6 with parameters G, -bt, and Ct.
So Q is fixed and known. Now, goal is to make our learnable process P match this fixed Q, right?
Precisely. Equation 7 shows how they set up P to mirror Q's form. They choose the initial state, PZ0, to be a standard Gaussian, which is, importantly, the stationary distribution of that Ornstein-Uhlenbeck process.
Okay, matches the long-term behavior of Q.
Exactly. And then the transition PCC1X is also defined as a Gaussian. But here's the learning part. The mean of this Gaussian includes our trainable neural network block, UTHIS1X.
The block we want to train.
Right. Remember, that block is conditioned on the input X. The variance of this transition in P is kept the same as in Q, the CT term.
And aligning P with Q, that gives us the actual training objective.
Exactly. You substitute this parameterization of P into the ELBO expression, do some math, and you arrive at the NoProp objective function. That's equation 8.
Okay, what does it look like?
It has 3 main components. First, a classification loss. This encourages the final state, ZUT, to be useful for predicting the correct label Y.
Makes sense. Need to predict something useful.
Second, there's a KL divergence term.
Yeah.
This basically makes sure the initial noisy state 0, 0 under our learned process P stays close to the prior distribution of 0 under Q.
Okay, keeps the starting point reasonable.
And third, there's the denoising loss. This term is really insightful and measures the square difference between the output of our neural network block, root, and the embedding of the target label. Let's call it I.
So it's trying to predict the label embedding from the noisy state.
Essentially, yes. And this difference is weighted by a signal-to-noise ratio, SNR. Now, the really key takeaway here is that each block is trained independently. It learns to predict the label embedding I given the noisy state ZT1 and the input X. And this happens without any forward or backward propagation across the whole network.
Wow. Okay, so truly layer local learning. Each block learns the same task based on its local input and the global target.
That's the core idea. It's fundamentally different.
It really is. Okay, so given this core concept, what are some of the interesting variations or extensions the researchers explored?
Yeah, they looked into several compelling variations. One key area is how they handle the class label representations, this embedding matrix, WEMBED.
Ah, how you represent cat versus dog.
Exactly. They considered cases where WEMBED is fixed, like just using simple one-hot encodings, but also cases where WEMBED is learned end-to-end along with everything else.
Learnable embeddings, okay.
And interestingly, when the dimension of this embedding space matches the dimension of the input images.
Like if the embeddings were the same size as the pictures.
Right. They interpret these learned embeddings as image prototypes for each class. They even have a neat way to initialize them using the median distance between images of the same class in the training set.
Huh, that's clever. Sort of finding an average-looking cat to start with.
Kind of, yeah.
And they also explored connections to continuous time models, like neural ODEs That seems like a natural fit.
It is. This is a really fascinating extension tying into, current trends. They look at what happens if you imagine the number of steps, t, becoming infinitely large.
Moving from discrete steps to continuous time.
Exactly. That leads to a continuous time formulation, which is in equation 9. Time t becomes a continuous variable, say, from 0 to 1. And you have a continuous noise schedule telling you how quickly noise is added.
Okay.
And instead of having t separate blocks, you train a single neural network block. This block takes the current noisy state, zits, the input x, and crucially, the current time t as inputs.
So one network handles all points in time.
Right. The evolution of ZIS over time then follows a continuous time diffusion process, which corresponds to a stochastic differential equation, or SDE. And that SDE often has a corresponding ordinary differential equation, an ODE.
Okay, connecting to the ODE literature.
But here's the kicker for training efficiency. In this continuous setup, training just involves sampling different time points, t, independently.
So you don't need to integrate the ODE forward and then backprop through the solver.
Exactly. You completely avoid backpropagating through the ODE solver, which is often a huge computational cost in training standard neural ODEs.
That's a big potential win. What about flow matching? You mentioned that too.
Yes, flow matching offers another angle on continuous time learning here. Instead of learning to reverse a noising process like in diffusion, flow matching directly learns a vector field, let's call it F. This vector field tells you how to smoothly transform an initial noise state, 0, into the embedding of the predicted label Z1, which is our U, by following an ODE.
So it learns the transformation directly.
Right. But since that transformation could be really complex, it actually learns a conditional vector field. This field depends on the starting noise 0, the target embedding Z1, the input X, and the current time T.
Okay, condition on the start, end, and input.
Yeah. Equation 10 shows a simple choice for the path connecting 0 and Z1, just a straight line path with Gaussian noise around it. This leads to a simple linear target vector field.
Makes it easier to learn.
Presumably. The objective for flow matching then is in equation 11. You train a network, VV, to predict this target vector field accurately.
Okay.
And when the label embeddings themselves are also being learned.
Right, the learnable Wimpy case.
They add an anchor loss, that's in equations 12 and 13. It includes a standard cross-entropy term based on a sort of extrapolated estimate of where the ODE flow will end up. This helps stop all the class embeddings from just collapsing onto the same point.
Keeps them separated. Makes sense. And the final prediction.
Similar to the other methods, the final predicted probability over classes, BOUT, usually comes from passing the final state through a linear layer and a softmax.
Okay, so we have these different takes. Discrete diffusion, continuous diffusion, flow matching.
Yeah.
What do the actual neural network architectures look like? The ones doing the work inside these blocks.
Right, the implementation details. Figure 1 in the paper gives a high-level view. For inference with the discrete version, NoProp DTT.
Yeah.
You start with random noise, 0, 0, pass it sequentially through t-learned blocks, EAT. Each block sees the input image X. This gives you Z1, Z2, up to ZT.
Okay, step by step.
Then ZT goes into a linear layer and softmax to give the prediction E. But remember, the key is, during training, each EAT block is trained totally independently.
Right, no crosstalk during training. What about flow matching inference?
For flow matching, the ET blocks represent the ODE dynamics. You integrate the ODE starting from noise, and the final prediction is usually made by finding which class embedding is closest, maybe using Euclidean distance, to the final state ZT.
Okay, and if we zoom in on the network inside a block, like OOT, what's in there?
Figure 6 in the appendix shows more detail for the discrete time network, OOT. It takes two main inputs, the image X and the latent variable ZT1.
Which is in the label embedding space.
Right. The image X goes through, say, a convolutional embedding module, then some fully connected layers.
Standard image processing.
Now, if the label embedding dimension happens to be the same as the image dimension.
The image prototype case.
Exactly. Then ZT1 is also treated like an image and goes through a similar convolutional path. If not, ZT1 goes through its own fully connected network, maybe with skip connections.
Okay, different paths depending on the setup.
Then the process representations of X and ZT1 are concatenated, fed into more fully connected layers, which produce some logits.
Logits. Okay.
Now, the actual diffusion dynamic OOT is calculated by taking a softmax over these logits. This gives a probability distribution over the class embeddings, and OOT itself is the weighted sum of the class embeddings using these probabilities as weights.
So it computes an expected embedding based on the logic.
Precisely. The continuous time version U is very similar structurally, but it also takes the time stamped to as input, usually encoded with positional embeddings.
Right, needs to know when it is.
And the flow matching network, VI, is similar again, but instead of the softmax, it directly computes the weighted sum for the vector field prediction. But the overall structure processing X, processing Z, or the noise, combining them is pretty consistent.
And the final classification layer.
Yeah, POW, that's typically just a linear layer followed by softmax applied to the final output of the respective network. ZT, or its equivalent.
Got it. You mentioned noise schedules earlier, crucial for diffusion. How did they handle that?
Good point. For the discrete time version, NoProp DT, they used a fixed cosine noise schedule. That's pretty standard and works well.
Okay, off-the-shelf schedule.
But for the continuous time version, NoProp CT, they actually learned the noise schedule during training.
Oh, interesting.
Appendix B has the details, but basically the signal-to-noise ratio is parameterized by a learnable function, RTT. This function is itself a small neural network, but with constraints to make sure its monotonically decreasing noise should generally increase over time.
So the model learns the optimal way to add noise over time. Cool. Okay, so NoProp offers this totally different paradigm. How does it stack up against other methods, both other backprop-free ones and standard backprop?
Yeah, the related work section is really useful here. They discuss several other backprop-free approaches. You've got the forward algorithm, target propagation, zero-order methods, evolution strategies.
Quite a few attempts then.
Right. And they point out that while these are interesting, they often have limitations. Maybe lower accuracy than backprop, maybe less efficient, sometimes tricky to get stable training, or hard to scale up.
Different trade-offs.
Exactly. Some rely on learning tricky inverse mappings, others might need tons of samples. A big plus for NoProp they highlight is that, unlike many others, it doesn't even need that traditional forward pass during training.
We keep coming back to that as a major departure. And how about its relationship to diffusion and flow matching themselves?
Well, they definitely acknowledge all the great work using diffusion for classification, regression, generation, and flow matching for various tasks.
Right, they didn't invent those.
No. Their main contribution, as they frame it, is taking these powerful ideas and specifically adapting and applying them in this new context. Back-propagation-free learning for image classification, leveraging those tools for a different goal.
Okay. This whole idea of not needing forward or backward passes, it really makes you think about representations, doesn't it? How is learning happening?
Absolutely. It's a deep question. For ages, the story in deep learning has been about hierarchical representations, right? Each layer builds more abstract features on the last.
It's standard view, yeah. Pixels to edges to objects.
Exactly. But the authors argue NoProp, at least in this form, doesn't really learn representations that way. It relies more on, well, user-designed representations.
Like the noisy label embeddings.
Yeah, or the interpolation path in flow matching. These intermediate states are defined by the method, not purely learned layer by layer from the data in the same way.
So it bypasses that hierarchical feature learning.
It seems so, which leads to a really fundamental question the paper kind of throws out there. Is that hierarchical learning actually necessary for good performance?
A big question.
Could we get strong results by perhaps carefully designing representations from the start, even if they aren't learned hierarchically? Maybe this opens the door to totally new kinds of deep learning models, ones with different properties, different trade-offs than backprop gives us.
That's incredibly thought-provoking. Okay, let's switch gears to the experiments. How did they test NoProp? What data did they use?
They used 3 standard image classification benchmarks.
Handwritten digits.
Yep, CFAR 10.
10 classes, small color images.
Right, and CFAR 100.
Similar, but 100 finer grain classes.
Exactly. Pretty standard test beds. They used the usual train-to splits, and importantly, they didn't use any data augmentation.
Okay, so a clean comparison of the learning algorithms themselves.
That seems to be the goal.
And how did they set up the different NoProp versions for these tests?
Okay, for the discrete time one, NoProp DT, they used T10 steps. Training involved updating the parameters for each step sequentially, following algorithm 1 in the paper.
10 independent blocks learning.
Right. They also tried 2 ways to get the final class probabilities from the last state ZT, the usual softmax after a linear layer, and an alternative based on radial distance to class embeddings.
Comparing output heads. What about baselines?
They had a backpropagation baseline, also with T10 layers, designed to be structurally similar to NoProp DT, but trained normally with backprop.
Okay, a fair comparison structure-wise.
For the continuous time versions, NoProp CT and NoProp FM, they used T1000 steps for inference to approximate the continuous process. But during training, they just randomly sampled time t.
Exploiting that continuous time training benefit.
Exactly. They also compared against another continuous time baseline called adjoint sensitivity, which also used T1000 steps for training and inference.
Okay, got the setups. Now the results. How did NoProp actually perform?
The main results are in Table 1, and they look pretty good for NoProp DT, the discrete version.
Yeah, I'll go over.
On all three datasets, MNIST, CIFAR 10, CIFAR 100, its accuracy was comparable to, and sometimes even a bit better than, the backpropagation baseline.
Wow, competitive with backprop.
Yeah, and maybe more significantly, it consistently beat the other backprop-free methods they compared it to.
Okay, so it leads the pack for backprop-free and holds its own against backprop. Any other wins?
Table 2 shows another potential plus. NoProp DT used noticeably less GPU memory during training compared to the backprop baseline.
That's always welcome.
Definitely. And Figure 2 has this cool visualization of the learned class embeddings for CIFAR 10, showing how they sort of evolve from the initial prototypes.
Nice. What about the continuous time versions? NoProp CT and FM.
Their accuracy was generally a bit lower than NoProp DT. The authors guess this might be due to the extra complexity of conditioning on the continuous time variable t.
Okay, maybe a trade-off there.
Perhaps. But as Figure 3 shows, these continuous NoProp versions generally did better and were more efficient than that adjoint sensitivity baseline, especially on CIFAR 10 and 100.
Still promising in the continuous space.
Seems so. Although, interestingly, they note NoProp FM struggled on CIFAR 100 with just one hot embeddings. It needed the learnable embeddings to perform well there.
Okay. Embeddings matter.
Yeah.
What about ablation studies? Did they dig into specific design choices?
They did. Figures 4 and 5 show this. They looked at those two ways of getting final probabilities, softmax versus radial distance.
Yeah. Which was better?
No clear winner, actually. It seemed to depend on the dataset which one worked best.
Huh.
They also looked at initializing the class embeddings in that image prototype setup, compared random init, orthogonal init, and their median distance prototype init. Both orthogonal and their prototype method seem generally as good as, or sometimes better than, just random initialization. So smart initialization helps, or at least doesn't hurt.
Okay, good to know. All right, let's try to wrap this up. If we synthesize all of this, what are the main conclusions we can draw from this deep dive into NoProp?
Well, I think the primary conclusion is that NoProp really does present a viable and, importantly, a performant alternative way to train neural networks. It completely gets rid of the need for both forward and backward propagation during training.
A genuine alternative paradigm.
Exactly. By using ideas from denoising, score matching, and diffusion, it's shown results better than other backprop-free methods, and it's even competitive with standard backprop, especially the discrete time version.
So for the AI researchers, the ML engineers listening or watching, what are the key advantages NoProp might offer them? Why should they care?
Several potential benefits, I think. First, no forward-backward passes could be huge for distributed learning, right? Laters learning more independently could really scale better.
Less communication overhead.
Potentially, yeah. Second, the method itself seems, well, conceptually maybe simpler and more robust than some other backprop-free ideas.
Okay.
And the experiments suggest real benefits in computational efficiency and lower memory use, which is always a big deal.
Absolutely. And thinking bigger picture, beyond just being a new algorithm, what are the broader implications here for deep learning?
I think the most intriguing thing is that NoProp gets good results without apparently relying on that traditional hierarchical representation learning.
Right, the point you made earlier.
It really forces us to question if that's the only way, or even always the best way, for deep networks to learn. Could we design representations more explicitly? Could local learning rules be more powerful than we thought?
It opens up new research directions.
Totally, exploring different kinds of deep learning models, ones that might excel where current backprop models struggle. It's exciting.
So for everyone tuning in, especially those working at the cutting edge, what's the final takeaway?
I'd say this NoProp paper is definitely worth reading closely. Think about how these ideas might apply to your own work.
Especially if dealing with distributed training or exploring non-standard architectures?
Yeah, for sure. Or if you're just interested in fundamental questions about learning representations, the fact that you can get strong results without the standard passes it feels like it could be signaling a shift, or at least the possibility of one.
Which leads us to our final thought for today. Could methods like NoProp be the start of something fundamentally different? A new era for deep learning, maybe? Moving past Backprop's limits and finding entirely new ways for AI to learn.
It's definitely a question worth pondering. A lot of research to be done there.
Indeed. Well, that's all the time we have for this deep dive. Thanks for tuning in to AI Paper Podcasts.
Catch you next time.